Hello class, welcome back to Introduction to Material Science and Engineering. Today we're going to be talking about the different ways in which material or atoms and small molecules get from one place in another material to another. This is going to take great advantage of all the concepts we've covered to date, namely defects in materials that we covered in our last section. So, looking at different types of mass transport, and that would also be atomic, molecular, moles of things transport. It doesn't have to necessarily refer to as mass per se, but material transport within a microstructure of another material. Three main ways. Diffusion, which is transport by atomic motion in response to what we'll deal with as a concentration gradient, but in a more general sense is termed a chemical potential gradient. There's convection, which is usually for fluids, and could be defined as fluid movement in response to a mechanical force. And in the case of charged particles and an electrical potential gradient, you can get charged species moving in response to that gradient. You might have noticed that migration and diffusion are pretty similar, and they are. Both of them involve a species moving in response to a gradient. Migration tends to be quite a bit faster. Now, one thing that this group of three description doesn't pull in is the fact that even if you have multiple means of mass transport operative in any scenario, you will always involve diffusion as one of them. So it ends up being limiting in every respect because it is the slowest of the three. So even if you're moving, say, a fluid in a process, a casting, or you're using a polymer injection molder or a reaction injection molding process for a composite layup with a thermoset, say, you might use convection to move your liquid polymer from one place to another, but at the boundary of that liquid with the underlying solid substrate, you'll be limited by diffusion because there's always a thin layer where convection and even electromigration doesn't operate because you're too close to the surface. And in that case, the remainder of your transport will be by diffusion. So diffusion's always there, and because it's the slowest, it's always limiting. If you're familiar with chemistry, you would call this the rate limiting step. So the nice thing is if we can understand and characterize the rate of diffusion of any material process, we've got a pretty good way to estimate the overall rate of the process itself. Then we know how much time it will take, how we can make it happen faster without changing something else we don't want, and maybe how much it's going to cost. So that's what we're going to explore in this chapter. Okay, starting with the simplest case of diffusion. This is interdiffusion in metal alloys. And we're mainly going to talk about atoms, or you could envision small molecules for this argument or this discussion. We're not going to get into ions because the need for charge balance can really literally slow down both the discussion and the rate of transport, and is usually better discussed with electromigration. So we're going to use metals mainly for our discussion here. So imagine that we have two bars of metals, say, we'll use copper and nickel again because we know they're very soluble. So assume that in this diagram we have like a cube of copper to the left and a cube of nickel to the right, and we're looking at it in cross-section, and the interface between the two is where the two cubes meet. If we were going to draw a concentration profile across this with right to left being like the x-axis on the graph on the bottom, and then percentage, mole percent of each of the different metals on the y-axis, you'd see 100% copper all the way up to the interface, and then 0% copper thereafter, and the opposite for the nickel. So the concentration profiles for each of the two different metals would effectively be step functions, 0 to 100. If we gave it a little bit of heat, increase the temperature to maybe half the melting point is usually a good benchmark for increasing diffusion rates, just as an aside, and we came back after some time, maybe a few hours, we would find this scenario. Some of the copper atoms would have diffused to the right, and some of the nickel would have diffused to the left, and rather than having a sharp step function defining the boundary, we would kind of have a smooth curve. Now, if these blocks were the size shown and we waited an even longer time, we would eventually get a uniform concentration all the way across. So we would go to whatever the equilibrium concentration was for those two, especially copper and nickel, that have infinite solid solubility. So now that we know what it wants to do, how does it actually get there? So we're going to start with the idea of vacancy diffusion, and this sets us up to understand how atoms that are solid solutions of one another interdiffuse. So if you remember back to our previous discussion about different types of solutes, you can have a solid solution alloy exist either on a lattice point of another material, where it's substituting for that on the lattice points, and again we use copper nickel for that argument, or you can have your solute atom fit into the crystallographic interstitial positions like carbon does in iron. So the idea of vacancy diffusion is very important for your substitutional solutes that need to diffuse. And the reason for this is, in order for one of them to jump from one position to another as they diffuse, they have to have a place to jump to. They can't co-occupy a lattice position. So looking back to our copper-nickel couple in our cross-section here on our diagram down at the bottom left-hand side of the page, you can see that we have one vacancy in our diagram. So that's really the only place any atom can jump to, because copper and nickel are about the same size. They can't exist in an interstitial position. So having that vacancy available after a certain amount of time, a copper atom will jump over and occupy it, and we will have this configuration. So we've had copper index over 1 to the right, and as a result it left a place, and now effectively the vacancy has diffused to the left. And now we have a free place for something else to jump, and now the vacancy's migrated up 1. This is very important for the rate of substitutional diffusion, because without a place to jump to, we can't get diffusion. So if you think back of the temperature dependence of vacancy concentrations, you can see that our diffusion rate might be dependent both on the jump frequency and on the concentration of vacancies. And those are both temperature dependent. So we have to have a place to jump to, and then we have to have a jump rate. So there's really a double dependency on temperature for substitutional diffusion. And what we just saw with the copper atom jumping to one vacancy and then another copper atom jumping, we just saw an example of substitutional diffusion. Now, the other mode in which things can move is interstitial. And so this would apply to, again, small atoms in a lattice of larger atoms. So if you are an interstitial solute, like carbon and iron, you will diffuse by jumping from one interstitial position to another. Now this is naturally much faster than substitutional diffusion, because effectively there's always a free spot to land in. There are quite a few empty interstitial positions in the average crystal. We discussed how many of those were present per unit cell. These are the 4F and the 6F holes that we discussed in our crystallography discussion. So an interstitial solute that is diffusing can jump to any of the unoccupied interstitial positions around it. So until you get close to filling all of those, which is rather rare occurrence, there's generally no need to wait for a position to be open. So there's effectively any position is open. So when you look at the rate of interstitial diffusion, what you're really looking at is just the rate at which that solute atom will jump, because it's always got a place to land. So there's a single dependence on temperature, and it's just the jump frequency, as opposed to substitutional diffusion, where you had the temperature dependence on the jump frequency and the vacancy concentration, which was the place to land. Okay, so now that we know that things want to diffuse in response to a concentration gradient, we have an idea of how they diffuse, either substitutionally or interstitially in a crystal lattice. Now we want to put some numbers on it. How long does it really take to get how much solute how far in or through something? Because that's how we design processes and pay for the energy to run them and understand how quickly we can produce parts and products that rely on diffusion, which, as we started with, ultimately is just about everything. So we need to define some terms that relate to diffusion rates. And the first term we're going to define is flux. And this is literally defined as the moles or atoms or molecules or mass that we're moving, we're diffusing, per area per unit time. So if you think about, say, water moving through a pipe of a given cross-section, if you look at the moles or mass of water per unit time per cross-sectional area of that pipe, that would be the flux of water through the pipe, just as an example. Now, having defined that, we move to probably the simplest and most widely used model of diffusion, and that's called Fick's first law. And it literally says that the flux of diffusing species is equal to the negative of a constant, called the diffusion coefficient, times the concentration gradient. So that's the change in concentration with unit distance. So it's not a time rate, it's a distance rate. This holds only when that concentration gradient does not change with time. And another way of saying an invariant or not changing with time concentration gradient is steady state diffusion. So when you hear someone say, this is steady state diffusion scenario, or this is diffusing at steady state, you know that you can use this very simple relationship. And the one thing I'll point out is it's not always obvious that the negative sign in front is intended to make sure that your species roll down gradient or roll downhill. Remember that your delta C over delta X or your dC dx, your concentration gradient, is a positive upward kind of orientation. So concentration is changing in a positive manner in that direction, and of course you're going to diffuse the other way. You don't diffuse from low to high concentration, you diffuse from high to low, and so that's why there's a negative sign in that equation. So this is a little bit of a graphical example of the equation. If you had a material with a region over on the yellow side that had a very high concentration of a particular species, concentration equal to C1, and over on the right-hand side you had a lower concentration, C2, and you had a region between them where that concentration was changing over a distance of x1 to x2, you would have a linear concentration gradient equal to C2 minus C1 over x2 minus x1. It's just the slope of that line, that red line between them. So if you basically squoze that x down infinitely small to take the derivative, you would get dC dx, and so that is the gradient that exists in Fick's first law. So if we do a little bit of a units analysis, just so we get ourselves oriented when we go to use the math here, you can see that flux will be in concentrations of species, moles, or atoms per unit area per unit time. And concentration gradient will be moles per unit volume for concentration, and then per unit length. And then that leaves the diffusion coefficient needing to be in units of length squared per unit time. And quite often you'll see your diffusion coefficients for metals especially being in units of centimeters squared per second. So the diffusion coefficient, with steady state diffusion you can increase your flux, get things to move faster either by increasing the gradient or increasing the diffusion coefficient. They have the same dependence in the equation, they're both linear dependence. With flux is linearly dependent on both. So quite often your process or your surface environment will determine the concentration. Maybe you're diffusing CO2 from the inside of your pop bottle to the outside. Those concentrations are fixed. There's not much you can do about it. So your only option as a material scientist is to change the diffusion coefficient of your material, possibly by re-engineering the material or choosing a different one. So if you are looking at any given temperature or any given material, your diffusion coefficient in a practical circumstance is dependent on parameters that are specific to the material, which are the activation energy, and your pre-exponent coefficient, which is just the diffusion coefficient at a fixed temperature, and then the actual temperature under which you're diffusing. This should look very, very similar to the equation for vacancy concentration, because your diffusion coefficient or your activation energy in this sense, at least in the case of substitutional diffusion, is in fact partially dependent on the vacancy concentration, the landing place. To a much lesser extent, the interstitial diffusion is temperature dependent, will have some dependence of its activation energy on vacancies simply because the lattice is more wide open, but not to the extent of substitutional. You can literally think of the activation energy for substitutional diffusion in metals as being a combination of your activation energy for vacancy creation and then another activation energy that represents jump frequency of those atoms trying to jump from one position to the other. We have the same trends with temperature. Higher temperature means faster diffusion. Higher activation energy means slower diffusion. So let's look at a few notable examples. On the interstitial side, we have carbon in either a BCC iron, which is alpha iron, or carbon in a face-centered cubic iron, gamma iron. They're in the purple. So if you're comparing those to each other, they overlap only across a small temperature range because iron actually changes stable phase from FCC to BCC as temperature drops below around 700 degrees C, depending on how much carbon is dissolved. But you can see the diffusion rates are comparable for the two, even though we've changed crystal structure, but generally a little bit higher in BCC. And that again has to do with the space between interstitial positions. Oddly enough, as an inverse, the FCC iron will dissolve more carbon, but it's a little bit harder to move it from one stable position to the other. The big difference you'll see is comparing any of those lower curves, the gray, the orange, or the red, to either of the two upper. The lower ones represent self-diffusion, which is by definition always substitutional. So aluminum and aluminum, alpha iron and alpha iron, or BCC iron, or FCC iron and FCC iron. So when you have to move something from lattice point to lattice point, the diffusion coefficient is much, much smaller because you now have to create vacancies to jump into. So it's that double temperature dependence, which also explains why those lines are steeper with respect to the x-axis because of the double dependence on temperature. Now, just looking at orders of magnitude, if we look at for the same temperature, the 1.0 on the x-axis in 1000 Kelvin degrees per temperature unit, you can see that the average iron in iron self-diffusion, a substitutional diffusion for the same temperature, is somewhere on the order of 5 orders of magnitude less than carbon dissolving in the same material. So that's another big glaring example of the difference between interstitial and substitutional diffusion, even for the same temperature. So what happens if things change with time? What happens if we don't have steady state diffusion? Well, lucky for us, there is another slightly less simple but a very reproducible relationship that describes concentration with not only concentration gradient, but with time. And this is called Fick's second law, and again it's for non-steady state diffusion, meaning the concentration gradient is changing with time. So the concentration gradient isn't always a straight line, and it does not stay the same with time. So you could read this in words as the change in concentration of your diffusing species with time is equal to the diffusion coefficient times the second derivative of concentration with with distance in the diffusing direction. And the example that you might work in the class is one particular solution to that differential equation. Of course, the second order differential equation that represents Fick's second law has many different solutions. Each one will result in a different set of equations relating distance, time, and concentration with diffusion coefficient, and it all depends on your initial conditions and your boundary conditions. One that is very frequently encountered in material science is constant surface concentration, constant bulk concentration, and inward diffusion of a given material. And this is used for surface treatments such as carburizing and nitriding and other types of scenarios where one species is diffused into the surface of another to create a hard or corrosion resistant layer at the surface, while leaving the overall properties relatively unchanged. So this is one way that we could create, say, a very hard, wear-resistant layer that has a lot of the properties of a ceramic without using a ceramic for a bulk, because obviously it's not so good for fracture. So those are called case hardening operations. So in this case, pun intended, for instance, say we have copper or atoms that we're going to diffuse into a bar of nickel or aluminum. Our CS represents our surface concentration, and we're going to keep that constant. We're going to electroplate a layer of copper over the top, so that very surface is constant. It's pure copper, it's 50-50, and we're going to keep it set there. And likewise, we're assuming that we're going to diffuse in deeply. So the bulk, the very center of the bar, is not going to change in concentration. It's going to stay the same, and that's C0 on our lower graph, meaning bulk or original concentration. And this kind of scenario where we have something that is so long that the interior concentration is not being changed by the action of diffusion is sometimes referred to as semi-infinite diffusion, because we're assuming that we could diffuse in an infinite distance and we're not going to change C0 with time. That will not always be true, but in most of our surface treatment scenarios and materials we can assume that. So if we started at 0 time, our bar only has C0. And our surface is C surface, of course, and so again we have that step function. And you can see that in sort of the pink line, which drops right from CS to C0 at time 0. And so we just have this, this big step. But if we, say again, gave it some temperature, increased our diffusion coefficient, and allowed that copper to start diffusing inward into the bar, at time 1, after some time, we would see that instead of a step function, we have a curve, a concentration gradient that has smoothed. And then at T2 and T3, that gets smoother and smoother, and the concentration of copper at any position inbound from the surface gets higher. And we are also seeing copper present further and further into the bar. Eventually, at t equals infinity, we wouldn't end up with a straight line across as we did in our finite thickness blocks that we started the chapter discussion with today, but we would have an unchanging curve that would effectively be the gradient by which the copper rolled into the material. And that at that point we would be back to the Fick's first law or steady state argument. So some rules of thumb for diffusion rates. Diffusion will always be faster when we have a more open structure. So for crystals, open structures are crystals with lower atomic packing factors, more open space. So BCC should be faster than FCC or HCP. Likewise, grain boundaries are going to be much, much faster than the centers of grains because they inherently, because of that mismatch that we discussed in our defects chapter, means that there is more open volume around the atoms. So there's literally more space for things to diffuse. Materials with weaker bonds, especially secondary as opposed to primary bonds, are going to have faster diffusion, both because they tend to have a little more open space, but mostly because the jump frequency is faster. Things aren't as fixed where they are. They're not in as stable an equilibrium position, so for any given temperature, they're more likely to jump and have an opportunity to diffuse. Smaller diffusing atoms are faster generally because they tend to have interstitial diffusion available under a wider range of circumstances. If it's substitutional diffusion, smaller doesn't necessarily mean faster. But smaller diffusing atoms will generally mean that it's more likely you have an interstitial path open to you, and those are, of course, as we saw, several orders of magnitude faster. Lower density does not have a direct correlation with diffusion, but it tends to correlate with a more open crystal structure and a greater fraction of secondary bonds. So it's an indicator, but not a direct mechanistic contributor. And of course, the converse is also true. Slower diffusion will be enhanced by closer packed structures, like your close packed crystallographic structures, eliminating grain boundaries in the direction of diffusion, materials with stronger bonds, like covalent bonds, and larger, bulkier diffusing atoms. One exercise that you might encounter is diffusion rates of different types of gas molecules through polymers. Bigger gas molecules diffuse much more slowly than smaller ones. One of the reasons why hydrogen is a big concern in diffusion. It is actually small enough to diffuse at room temperature through certain metal lattices and cause all kinds of problems, some of which we will touch on in fracture later on. So that is it for mass transport. We will be relying on all of the concepts that we've learned in these 6 chapters to now looking ahead, define constants and coefficients for our various mechanical properties, both for material deformation and fracture. Starting with next chapter, chapter 7, we'll be moving into a little bit more quantitative discussions, less mechanistic, but all of the constants and all of the trends, again, all of the coefficients that we'll use in our equations will be drawing on all of these concepts that we've learned somewhat qualitatively up till now. So, we will see you then.